Hello friends, welcome to EC Academy.
In this lecture, let us understand the switching characteristics of CMOS inverter. The main question in this topic is very simple. When the input of the CMOS inverter changes, how much time does the output take to change? In an ideal circuit, we may imagine that the output will change immediately when the input changes. But in a real CMOS circuit, the output cannot change instantaneously. There is always a capacitor that is connected at the output. This capacitance is known as load capacitance, and this capacitance has to charge and discharge. Therefore, charging and discharging of the load capacitance determines the switching speed of the CMOS gate. Therefore, the charging and discharging of the load capacitance determines the switching speed of the CMOS gate. This is very important concept to remember. Here, the capacitor determines how much charge has to be moved, and the transistor determines how quickly that charge has to be moved. Therefore, CMOS switching speed mainly depends upon the load capacitance and the transistor strength. Here, you need to remember the CMOS switching is basically charging and discharging process. Now let us understand this concept in detail. Now let us understand the inverter with load capacitance. First, let us look at this CMOS inverter. Here, we have two transistors. Transistor T2 is the PMOS transistor and transistor T1 is the NMOS transistor. The source of PMOS transistor is connected to VDD and the source of NMOS transistor is connected to ground. Both transistors gate are connected with the input, which is Vin. The drain of PMOS and NMOS are connected together and the common point is the output voltage, which is V0. Now we have a capacitor that is connected at the output. This capacitor is represented by CL, which is load capacitance. So what does this load capacitance represent? It represents the input capacitance to the next CMOS gate. So it can represent the output capacitance for the present gate and it can represent the input capacitance to the next CMOS gate. And this load capacitance can also include the capacitance of interconnecting wires. Therefore, CL represents total effective capacitance that is connected to the output node. Now let us understand the operation of a CMOS inverter using the waveforms. Suppose the input voltage Vin is low, the PMOS transistor T2 will turn on and the NMOS transistor T1 will turn off. Therefore, output is connected to VDD through PMOS transistor. The capacitor CL get charged. Therefore, the output voltage will become approximately equal to VDD. So, V0 is approximately equal to VDD as shown in this diagram. Now suppose if the input voltage changes from low to high, the PMOS will turn off and NMOS will turn on. At that case, the output will be equal to 0 since output is connected to ground through NMOS. Since output voltage is 0, the load capacitor starts discharging. Hence, the output voltage starts decreasing towards 0. So, output voltage will approach 0. So, when Vin is low, then V0 will go to high due to capacitor charging, and when Vin moves from low to high, the output will move from high to low since capacitor is discharging. You can observe that the input is changing instantaneously from low to high and high to low, but the output does not change instantaneously. As you can see, it is taking some time to move from high to low and from low to high. So the output takes some time to fall and it also takes some time to rise. So why does the output take some time to fall and rise? Because the load capacitor has to charge and discharge. So you need to remember the output transition takes some time because load capacitor has to be charged and discharged. So this is the fundamental reason for switching delay in a CMOS circuit. So remember, CMOS switching speed is fundamentally a capacitor charging and discharging problem. This is very important point to remember. Now let us look at the key definitions. We have a rise time that is represented by TR. Rise time is the time required for the output voltage to rise from 10% to 90% of the final steady state value. Therefore, rise time is the time required by the output to change from 0.1 VDD to 0.9 VDD. So you need to remember the rise time is the time taken by the output to rise from 0.1 VDD to 0.9 VDD. Next is fall time represented by TF. Fall time is the time required for the output voltage to fall from 90% to 10% of its steady state value. Therefore, fall time is the time required by the output to change from zero point 0.9 VDD to 0.1 VDD. So you need to remember the difference. Rise time means 10% to 90% rise. Fall time is 90% to 10% fall. Next is delay time represented by TD. Delay time is the time difference between the 50% transition level of the input and the corresponding 50% level of the output. So delay time is the 50% transition level of input and the 50% transition level of the output, and this difference is known as a delay time. So why do we take this 50% transition time? Because it provides the convenient reference point near the middle transition. Exactly at the middle, we will have a convenient point where we can measure the delay time. So you need to remember, fall transition, the output changes from high to low, and the transition from 0.9 VDD to 0.1 VDD is fall time, and the delay associated with the fall time is TDF. Similarly, during rise transition, the output will rise from 0.1 VDD to 0.9 VDD. This will give the rise time TR, and the delay associated with rise time is TDR. So remember these three terms. Rise time will tell us how fast the output rise. Fall time will tell us how fast the output falls, and delay time gives us the propagation delay that tell us how long the output takes to respond to the input transition. Now let us understand equivalent circuit for fall time. So this is the analysis of fall time. Suppose the input changes from low to high, then the NMOS will turn on and PMOS will turn off. Therefore, the load capacitor CL starts discharging. Then the output voltage V0 falls from high voltage to low voltage. But you need to remember one important point, that NMOS transistor does not remain in the same operating region throughout the entire discharge. The discharge takes place in two regions. First one is a saturation region and second one is a linear region. Therefore, we have fall time for saturation region as TF1, and fall time for linear region we can take it as TF2. Therefore, total fall time will be equal to TF1 plus TF2. Now, let us derive the equation for TF1, then we will derive for TF2. and we'll add these two values to get the total fall time, which is TF. Here TF1 is the time spent in saturation region, TF2 is the time spent in a linear region. Now let us understand these two regions separately. Now let us understand fall time saturation region. In saturation region, PMOS will be off, NMOS will be on, and it is represented by the current source IDN. The capacitor CL is connected at the output. The output voltage that is measured across the load capacitor. Initially, the output will be very high. During this part, the capacitor starts discharging and the NMOS will be operating in saturation region. In this condition, V0 will be greater than VDD minus VTN. So in saturation region, V0 will drop from 0.9 VDD to VDD minus VTN. So during discharge of the capacitor, the differential equation can be given as minus CL dV0 divided by dt will be equal to 1 by 2 beta n VDD minus VTN whole square. Here beta n represents the strength of NMOS transistor, VDD is the supply voltage, and VTN is the threshold voltage of NMOS. Now, in this equation, let us separate the variable so that we will get the equation for a dt. So, we can write the equation as dt is equal to minus 2CL divided by beta n into VDD minus VTN whole square dV0. Now let us integrate on both sides and let us take the time as t is equal to 0 to t is equal to TF1 and voltage V0 is equal to 0.99 VDD to VDD minus Vin. Since the output voltage is falling from 0.99 VDD to VDD minus Vin, we will take this as integration limit. So above equation we can write it as integration of 0 to TF1 dt will be equal to minus 2CL divided by beta n VDD minus VTN whole square. Integration from 0.9 VDD to VDD minus VTN of dV0. So in the above equation, this entire term represents constant. That's why we'll take outside the integration. So if we integrate both sides, we'll get t between the limit 0 to TF1 will be equal to minus 2CL divided by beta n into VDD minus VTN whole square. So if we integrate dV0, we'll get V0. So we can write V0 between the limits 0.9 VDD to VDD minus VTN. If we substitute the limit values in the above equation, we will get TF1 minus 0 will be equal to minus 2CL divided by beta n VDD minus VTN whole square multiplied with VDD minus VTN minus 0.9 VDD. So if we simplify the above equation, we will get TF1 will be equal to minus 2CL divided by beta n into VDD minus VTN whole square. Now if we simplify this term, we will get 0.1 VDD minus VTN. Now if we multiply this negative term along with this term, we will get the numerator as TF1 will be equal to 2CL into VTN minus 0.1 VDD divided by beta n into VDD minus VTN whole square. So this is the fall time for saturation region. Now let us understand the fall time for linear region, where the output will be between 0 and VDD minus VTN. So in this linear region, the output will drop from VDD minus VTN to 0.1 VDD. In the linear region, the NMOS transistor can be approximated as a voltage dependent resistance. So in this region, the capacitor is still discharging. However, the current flowing through this is no longer constant. Now let us understand the fall time of linear region. In linear region, the output falls from VDD minus VTN to 0.1 VDD. During discharging of transistor, we can write minus CL dV0 by dt will be equal to beta n into VDD minus VTN multiplied with V0 minus V0 square divided by 2. If we rearrange the above equation and if we write the equation for dt, we will get dt is equal to minus CL divided by beta n multiplied with dV0 divided by VDD minus VTN into V0 minus V0 square by 2. Now let us set the integration limit from TF1 to TF1 plus TF2 on time, and output voltage V0 from VDD minus VTN to 0.1 VDD. So why we have taken this limit for voltage? Because in linear region the voltage drops from VDD minus VTN to 0.1 VDD. So we can write the above equation as integration from TF1 to TF1 plus TF2 dt will be equal to minus CL divided by beta n, which is constant, will be taken out of the integration. Then integration from VDD minus VTN to 0.1 VDD of dV0 divided by VDD minus VTN multiplied with V0 minus 1 by 2 V0 square. So for this right side equation, we can use the integration rule, which is integration of dx divided by ax minus 1 by 2x square can be written as 1 by a ln x divided by 2a minus x. And in the left side, if we apply the limit and if we integrate, we will get TF2. Therefore, we can write the above equation as TF2 will be equal to CL divided by beta n into VDD minus VTN multiplied with ln of V0 divided by 2 VDD minus VTN minus V0 between the limits VDD minus VTN
to 0.1 VDD. Here in this equation we will have a negative sign here. As you can see, you need to write a negative sign, and to nullify this negative sign we can interchange these two integration limit, or we can say we can invert the upper and lower integration limit. So we can write the above equation as TF2 will be equal to CL divided by beta n into VDD minus VTN multiplied with ln V0 divided by 2 VDD minus VTN minus V0 between the limits 0.1 VDD and VDD minus VTN. So if you substitute the upper limit in the ln for V0 is equal to VDD minus VTN, then in the above equation we will get ln 1, so that is equal to 0. And if you substitute the lower limit in this equation, where if you take V0 is equal to 0.1 VDD, at that case we will get the equation as minus ln 0.1 VDD divided by 1.9 VDD minus 2 VTN. Here it will be this term minus this term, so you will get this equation after simplification. So we can write the above equation as TF2 will be equal to CL divided by beta n into VDD minus VTN multiplied with minus ln 0.1 VDD divided by 1.9 VDD minus 2 VTN. Here you need to remember minus ln x by y, we can write it as ln y by x. So here to eliminate this negative sign we can use this formula. Therefore we can write TF2 is equal to CL divided by beta n into VDD minus VTN into ln 19 VDD minus 20 VTN divided by VDD. So here we have used this formula and inverted this term and multiplied by 10 to get this equation. Therefore we know total fault time will be equal to TF1 plus TF2. So this is the equation for TF2, and if we add TF1 and TF2 we will get TF is equal to CL divided by beta n into VDD minus VTN multiplied with 2 VTN minus 0.1 VDD divided by VDD minus VTN plus ln 19 VDD minus 20 VTN divided by VDD. Now if VTN is approximately equal to 0.2 VDD, so if you replace VTN with 0.2 VDD, this term will simplify to 0.25 and this term will simplify to ln 15. Therefore TF can be written as CL divided by 0.8 beta n VDD multiplied with 0.25 plus ln 15. If we simplify this, TF will be approximately equal to 3.7 CL divided by beta n into VDD. So we can approximate the fall time to 4CL divided by beta 1 into VDD. So this is the approximate value of fall time. Now let us understand the equivalent circuit for rise time. Now if the input of CMOS inverter changes from high to low, what happens? The NMOS will be off and PMOS will be on. Now PMOS will provide the charging path for load capacitor CL. Therefore, the capacitor CL will charge towards VDD. As a result, the output voltage will rise from a low to high. So, for rise time, the transition will take place in two regions. First one is saturation region and second one is linear region. So, the rise time for saturation will be TR1 and rise time for linear region will be TR2. Therefore, total rise time will be equal to TR1 plus TR2. Now we will understand the rise time for saturation region. In rise time, PMOS will be on and NMOS will be off. So the PMOS is represented by a current source. So this current will charge the capacitor CL. The output voltage will increase with a time since capacitor is charging. When the capacitor is charging, the saturation current CL dV0 divided by dt will be equal to 1 by 2 beta P into VDD minus absolute value of VTP whole square. Here beta P represents strength of PMOS transistor, VDD is the supply voltage and VTP is the threshold voltage of PMOS. Now let us rearrange this equation and derive the expression for dt. Therefore, we can write dt will be equal to 2CL divided by beta P into VDD minus absolute value of VTP whole square dV0. Now let us integrate by taking the limit t is equal to 0 to t is equal to TR1 for time and for voltage V0 is equal to 0.1 VDD to VDD minus absolute value of VTP. So we can write the above equation as integration from 0 to TR1 dt will be equal to 2CL divided by beta P into VDD minus absolute value of VTP whole square outside the integration because it is the constant value. Integration from 0.1 VDD to VDD minus absolute value of VTP dV0. If we integrate and apply the limit value, we will get the above equation as TR1 will be equal to 2CL divided by beta P into VDD minus absolute value of VTP whole square multiplied with VDD minus absolute value of VTP minus 0.1 VDD. If we simplify the above equation, we will get TR1 is equal to 2CL into 0.9 VDD minus absolute value of VTP divided by beta P into VDD minus absolute value of VTP whole square. So this is the equation for rise time for saturation region. Now let us understand the rise time for linear region. After the output reaches the value VDD minus absolute value of VTP, the PMOS will enter the linear region. Hence, the PMOS will be represented by a resistance. In linear region, the capacitor still continues to charge and output voltage continues to increase. Now let us understand the equation for rise time in linear region. In linear region, output voltage V0 rises from VDD minus absolute value of VTP to 0.9 VDD. At that case, the PMOS will be operating in linear region. Therefore, we can write CLdV0 divided by dt will be equal to beta P into VDD minus absolute value of VTP multiplied with VDD minus V0 minus VDD minus V0 whole square divided by 2. For simplification, let us take V shift as VDD minus V0, and if we differentiate, we will get dV shift will be equal to minus dV0. When V0 is equal to VDD minus absolute value of VTP, at that case V shift will be equal to absolute value of VTP, and when V0 is equal to 0.9 VDD, at that case V shift will be equal to 0.1 VDD. So we have done all this to simplify the integration mathematics. So if we substitute the V shift value in the above equation, we will get minus CL dV shift divided by dt will be equal to beta P into VDD minus absolute value of VTP into V shift minus V shift square divided by 2. If we rearrange the other equation, we will get dt will be equal to minus CL divided by beta P into dV shift divided by VDD minus absolute value of VTP into V shift minus 1 by 2 V square shift. Now, if we apply integration for time from TR1 to TR1 plus TR2 and for voltage from absolute value of VTP to 0.1 VDD. Therefore, we can write this equation as integration of TR1 to TR1 plus TR2 dt will be equal to minus CL divided by beta P integration from absolute value of VTP to 0.1 VDD dV shift divided by VDD minus absolute value of VTP into V shift minus 1 by 2 V shift square. So if we integrate this term, we will get TR2. So we can write TR2 will be equal to, now to eliminate this negative sign, we can interchange these two integration limit and we can write the equation as CL divided by beta P integration of 0.1 VDD to absolute value of VTP dV shift divided by VDD minus absolute value of VTP multiplied with V shift minus 1 by 2 V shift square. So we can use the same integral identity where integration of dx divided by ax minus 1 by 2 x square will be equal to 1 by a ln of x divided by 2a minus x. So here A will be equal to VDD minus absolute value of VTP. So if you use this formula in the above equation, we will get TR2 will be equal to CL divided by beta P into VDD minus absolute value of VTP multiplied with ln of V shift divided by 2 into VDD minus absolute value of VTP minus V shift between the limit 0.1 VDD to absolute value of VTP. So if you apply V shift is equal to absolute value of VTP in the above equation, we will get ln of absolute value of VTP divided by 2 VDD minus 3 absolute value of VTP. And if we apply the lower limit 0.1 VDD in place of V shift, we will get the lower limit as ln of 0.1 VDD divided by 1.9 VDD minus 2 absolute value of VTP. So if we take this as x and if we take this as y, ln x minus ln y will be equal to ln x by y. So we can write the above equation as TR2 will be equal to CL divided by beta P into VDD minus absolute value of VTP into ln of 19 VDD into absolute value of VTP minus 20 absolute value of VTP whole square divided by VDD into 2 VDD minus 3 absolute value of VTP. So this is the equation for rise time 2, which is the rise time for linear region. Therefore TR is equal to TR1 plus TR2. Therefore we will get TR is equal to CL divided by beta P into VDD minus absolute value of VTP into 2 into 0.9 VDD minus absolute value of VTP divided by VDD minus absolute value of VTP plus ln of 19 VDD into absolute value of VTP minus 20 absolute value of VTP square whole divided by VDD into 2 VDD minus 3 absolute value of VTP. In the above equation, if we put the absolute value of VTP as approximately equal to 0.2 VDD, so we will get TR is equal to CL divided by beta P into 0.8 VDD into 2 into 0.9 VDD minus 0.2 VDD divided by 0.8 VDD plus ln of 19 into 0.2 VDD square minus 20 into 0.04 VDD square divided by VDD into 2 VDD minus 0.6 VDD. Now this term will be simplified to 1.75 and this term will simplify to ln of 2.14. So we can write the above equation as rise time is equal to CL divided by beta P into 0.8 VDD multiplied with 1.75 plus ln of 2.14. So if we simplify this, we can write TR is approximately equal to 3.14 CL divided by beta P into VDD. Therefore, we can write rise time is equal to 4 CL divided by beta P into VDD. So, this is the total rise time.
Now let us compare the rise time and fall time. We have fall time approximately equal to 4CL divided by beta n VDD, and we have rise time approximately equal to 4CL divided by beta P into VDD. Both the formulas look same. Now for equal size transistors, approximately beta n will be equal to 2 times beta P. Now here, why beta n is greater than beta P? Here beta n is larger. The reason is the carrier mobility. The electron mobility is higher than hole mobility. Therefore, mu n will be greater than mu P. This is because electrons move more easily through the NMOS than holes moves through the PMOS. Therefore, for the same transistor dimension, NMOS is stronger. That's why beta n is 2 times beta P. Therefore, the rise time TR is approximately equal to 2 TF. This means the rise time is approximately equal to twice the fall time for equal sized transistors. If we say equal sized transistors, which means the size of NMOS and PMOS are same. So here NMOS is stronger due to electron mobility. So NMOS is stronger because the electron mobility is good, and PMOS is weak due to hole mobility, which is lower. So you need to remember, electron mobility is greater than hole mobility. That's why NMOS is stronger compared to PMOS. Therefore, rise time will be normally greater than fall time. Now we want to make this rise time and fall time approximately equal. So how can we do this? We need to make PMOS stronger by making PMOS wider. So we make PMOS wider. Therefore, the balancing condition will be beta P should be equal to beta n. So to obtain this, a common design approximation is that we make WP approximately equal to 2 times Wn. This will increase the strength of PMOS. So for this condition, rise time will be approximately equal to fall time. So you need to remember this design rule. A common approximation is WP will be approximately equal to 2 times Wn. This will equalize the rise time and fall time, that will make the PMOS stronger. Now let us understand delay time, which is propagation delay. The rise time tells us how quickly the output moves from 10% to 90%. The fall time tells us how quickly the output moves from 90% to 10%. But the propagation delay tells us how long the output takes to respond to the input. Here, the rising propagation delay can be given as TDR is equal to TR by 2, and falling propagation delay can be given as TDF is equal to TF by 2. So rising propagation delay is therefore related to the rising time, and the falling propagation delay is related to falling time. Now we can define average gate delay, that can be represented as tau average will be equal to TDR plus TDF divided by 2. So this will be equal to TR plus TF divided by 4. So in this formula we have substituted the value of TDR and TDF to obtain TR plus TF divided by 4. So this is one of the important formula. You need to remember the average gate delay will be equal to rise time plus fall time divided by 4. Now from this we can understand that if rise time and fall time are small, the average gate delay will be less, and if rise time and fall time increases, the average gate delay will also increase. Therefore, balanced transistor sizing is important. So this is about switching characteristics of CMOS inverter. Hope you have understood the topic. Thank you.